Then let's get this started. Welcome to the talk about performance and optimization in Unity. Quick snippet about me, I'm Rene. I've been with Unity for about 2.5 years now. I'm based out of Copenhagen and I work on the core team, doing mostly low-level stuff like memory and loading and threading and all that kind of stuff. I did most of the work for the 64-bit editor. I've worked on threading for IL2CPP for the past couple of weeks. And when I get back, I will actually work on the new input system. So, yes. As far as the topics of this talk are concerned, this is going to be mostly about memory stuff, about loading things, this kind of stuff. So, yeah, let's get started. So when optimizing your game, there's like several different dimensions along which you normally optimize. The most obvious one, of course, is frame rate. So usually you would target your game towards a specific level of frame rate that you want to achieve, like 30 or 60 FPS. What you get there is entirely determined by two factors, like the amount of time you spend on the CPU and the amount of time you spend on the GPU. And the limiting factor of the two is the one that actually drives your frame rate. So if the GPU is slow, the GPU drives your frame rate. If the CPU is slow, it will drive your frame rate. This is important for optimization. So if you optimize for CPU, for example, and you're not actually CPU bound, you won't get any speed up. A second dimension is hiccups, like you want smooth gameplay where frames take roughly the same amount of time. You don't want a frame that suddenly takes a lot more time than the frames around it, because then you get a spike in gameplay, a noticeable lag that the user will actually see, very bad in games that require fast feedback. And this is what you usually get, and that you usually see when you have processes that either run infrequently, like the garbage collector, or processes that may suddenly take much more time than they usually do. Like, say you move a static collider, and then the physics update will take much more time than usual, and you will see one frame spiking out in between the other frames. A third dimension is memory. You want to optimize for size, obviously, on resource-constrained devices, not use more memory than you have. But also, you want to optimize for memory activity. So you want to keep the memory activity low, so that the memory subsystem doesn't consume a lot of time. The tool that we have in Unity to actually find where you are spending your time is the profiler. And the profiler allows you to monitor and look into different subsystems in Unity using different kinds of views. The two that we will be focusing on in this talk is the memory view and the CPU view. But you have much more views, like you can look at what the audio system does, what the physics system does, and so on and so forth. It used to be a pro-only feature in Unity 4X, but now, like with Unity 5, you can use the personal edition. It's available to everyone. So the profiler is now available without restrictions. So let's start by looking at the CPU profiler. The CPU profiler allows you to look at where you actually spent your time on the CPU within the frame. It gives you a detailed breakdown of what methods and what profile regions actually take up time, and you can sort them by the amount of time they take so that you can focus on your bottlenecks. And you can nicely drill down because it's a hierarchy. Also, it has a column that shows you the garbage collection or the memory allocation activity within that region, so that you can know, okay, which methods or which regions are actually allocating memory. These are the ones you want to focus on in order to keep memory activity down, but we will look at that in more detail later. Also, the profiler actually allows you to connect to the game as it is running on your device, which is something that you will pretty much always want to do in practice. Like profiling things in the editor is useful to some extent, but it's not giving you a picture of what really happens on the device. So start the game on the device, connect the profiler, or use the build and run option with auto-connect profiler to connect the profiler as it runs on the iPhone or standalone or whatever. In the editor, you also have the option of enabling deprofiling, which is basically a mode where we instrument each and every script method. It is pretty expensive, so on larger projects and bigger scenes, it's you usually run out of memory. So it may or may not work. You have to try it, but it can be very useful because it gives you a lot of data. One thing that is new in 5 is the new timeline view in the CPU profiler, which allows you to see where in relation to each other things are actually being worked on, also with all the different threads, including all the worker threads internal to Unity. So you can see exactly, okay, when are methods actually running within the frame in relation to each other, which is pretty useful for finding out scheduling or synchronization issues. Okay, so let's move on to the memory profiler. The memory profiler has a simple view, which just gives you a raw breakdown of where all the different memory inside of Unity goes. Just raw numbers. It has, for example, for Unity as well as for Mono, a breakdown of the memory that we have reserved and the memory that we're actually using. Like what happens is that Mono, as well as Unity itself, will request memory from the OS, and then from that big chunk, take out smaller portions to satisfy individual requests. The number that we show for the GFX driver, that's actually, it's just an estimate. Like we monitor the data that we send to the GPU, and based on that, give you an estimate of how much GPU memory we're actually using. But it's not really something that we request from the device and show based on the actual usage reported by the driver. A different view is the detailed view, which allows you to go much more in depth in terms of finding out, okay, what are the objects that are actually live, where are they referenced, where like is the distribution of all the data that goes into the different places. So this thing is pretty expensive to collect, which is why we don't do it live all the time. You have to explicitly say take snapshot to get the breakdown, and then you can drill down and see all the objects as well as all the internal chunks of memory that we have. Also, on the right, you will see, if you select an object, all the places that the object or that the piece of memory is actually referenced from. This is especially useful if you have leaks in your game where the data is not being collected by the garbage collector because it's still referenced somewhere. Then you can go in there and see, okay, well, this texture is still being used here even if it shouldn't be, and then clear out the references. Okay, so from there, let's actually start talking about loading for a bit. Just as a quick overview, what are the kinds of data that we're actually dealing with in Unity? There's the obvious things like scenes and the assets they depend on, such as meshes and textures and shaders and so on and so forth. But then there's also all the stuff that you can put into the resources folder, that you can put into streaming assets, or that you can download through dub. And with these mechanisms, you actually have easy options to build your own completely custom loading pipelines. Like you can, for example, drop a file into streaming assets and then use the standard .NET I/O facilities to just load it from there and do whatever kind of loading that you want to do. But what you would normally do is you use the loading facilities inside of Unity. With these facilities, you pretty much always have the choice between loading synchronously and loading asynchronously. Synchronously, from a programmer's perspective, is always desirable because you have a very clear sequence point. You can put whatever you need to do in order to get into clean state. You can put that there, like garbage collection, warming up your subsystems, whatever you want to do. And then once you're in clean state, you start your game. But the problem is you keep the player waiting, so it's not really always an option. So for all these cases, we have asynchronous loading APIs. So whether you load a level, whether you load assets, or whether you load resources, all these APIs are available in asynchronous variants. In 5.0, we added resources.load async. Previously, you could load resources only synchronously. So now, for all the different loading APIs, we have asynchronous variants. One thing to keep in mind, though, is that the total size or total amount of data that you load in the background still matters. Even though it would seem like if you load in the background, things should just come in smoothly whenever they are available, the reality is that we load up all the objects in the background, and then we have one integration step on the main thread where we go and register all these objects and activate them. And it depends pretty much on the types of objects that are being activated, but some types of objects, for example, meshes, have pretty costly activation steps directly on the main thread. So if you have a huge number of assets in there, even though they come in from the background, from the loading thread, they still activate all in one bulk on the main thread. So even though you load asynchronously, you may still see a hiccup in gameplay when these objects are being activated. So in that case, try to load things in smaller batches, space them out over time to get rid of the hiccups. One thing we did in 5 is that we actually moved the texture loading to background thread, or actually to the render thread. So now the textures, even though their objects are being activated, they don't need their data yet. So it's only when they're actually rendered and picked up by the graphics system that they are being waited on. And usually by then the data is there. So they can just continue loading in the background. And this is something that we want to do for more and more types of assets. Right now it's only true for some. Like substances will do that as well. Okay. A different thing when you're loading scenes. One potential problem that you may encounter is memory spikes. And the reason for that is that we only get rid of the data from the previous scene when the data for the new scene is completely available. So we load the objects for the new scene in the background, and then we have a step that basically activates them on the main thread. And only at that point, we delete the game objects from the previous scenes. But that's still only the game objects. The assets, they will stick around until one frame later. So we do a garbage collection on the assets only one frame after the new scene has been completely loaded. So for a short amount of time, you may actually have all the script memory for all the old game objects, as well as the memory for all the assets present at the same time. And this may lead to a pretty significant spike in terms of memory use. One solution to that problem is to just put a transition scene between the old one and a new one. So you load your intermediate scene, which may be like a loading type screen or some empty thing or whatever. You load that, and then you load the new scene. And that first gets rid of all the old assets and all the old stuff, and then you load the new stuff. The downside is that you may end up unloading assets that are used by both the old scene and the new scene. One thing that you will get later in the 5x cycle is a new API for loading and unloading multiple scenes. So there you can unload an existing scene just with a single API call, and that will make the whole transitioning process, when going from one scene to the next one, quite a lot smoother. So a different topic in loading, of course, is serialization. In case you're unfamiliar with the term, it's what we refer to when we take object graphs and either linearize, turn them into linear representation in memory or on disk, either in textual form or in binary form, and then convert that representation back into an object graph. In Unity, we use our own internal serialization system, which, that's the good news, is it is pretty fast. There is, however, a path in there which is pretty slow, which is the backwards compatible path. This is used in the editor all the time. Like when we load all old Unity data, we still want to be able to load that even in the newest version of Unity. But in the player, this only happens when you have data that was built with the previous version of Unity, and is loaded into a player that was built with a newer version of Unity. In most cases, that is impossible. However, with asset bundles, it is. Also with a web player, with the old web player, not WebGL, it may also happen. So in that case, we go back to a loading path which is pretty slow. So if you upgrade your player, it may make sense to also like re-export all your asset bundles, redeploy them, so that they are guaranteed to load fast. One problem that we used to have is that serialization of script data used to be pretty slow. And the reason for that is we need to go to .NET reflection data in order to be able to find out, okay, what are the fields and what are the types that we actually need to serialize. And we used to do that on the fly. So as we came across the data, we looked up all the .NET reflection data. What we've been doing since, I think, Unity 4.5 is to actually build up a cache, look up that data once, and then reuse the cache over and over and over again. So the cost of lookup, you pay only on the very first script object of a certain type, and then afterwards, serialization of script objects is actually pretty close in performance to native objects. Some platforms that don't allow direct memory-to-memory transfers have their own complete custom system, which is actually based on code generation at build time, and then we put that generated code into the player assembly. They don't have that problem anyway. A side note here, something that we started using a while ago is a form of data where we can basically map the data on disk right into memory without any kind of post-processing. And just as soon as the data is there, we can go. We use that in Mechanim at the moment, but we want to use that in more and more subsystems because that's the ultimate and the fastest way to actually load stuff. So another thing, loading, unavoidable topic, asset bundles. Asset bundles don't give you any speed up in terms of loading things faster, but they do give you access to different kinds of optimizations. The most important one is build size optimization. So you get your player size down, which is quite important if you upload to a store with size restrictions. But a side effect of that is actually that you also get much faster build times. So you can iterate faster. Because the player is smaller, takes much less time to build the player, and you can download it to the device faster. So even just for your own workflow, it may be actually useful to use asset bundles and move assets away out of the player into bundles. Asset bundles, while they are loaded, have a certain memory overhead. We used to have some pathological cases there where we had to have the entire asset bundle in memory while it was being loaded. That's not the case anymore, except in cases where we really cannot use the cache at all, and we really have to keep the entire thing in memory. A small tip here, like if you download the asset bundle through www, make sure to use this method here, like load from cache or download. The reason is that www by default goes and caches the entire data that it downloads, because there's the bytes property, which gives you access to that data. But when you download asset bundles, you really don't want that to happen, because if you have like an asset bundle with tens of megabytes, you would pay that cost directly in memory. With this method, we disable that mechanism. You actually cannot use the bytes property in that case, and make sure that the asset bundle, as we download it, goes straight to the cache and not to memory. Finally, for loading, let's also talk about unloading, because once you brought the data in, you also need to get it back out. With 5.0, one thing we did was we made object deletion much, much faster by moving the bulk of the work away from the main thread into its own thread. So we have a small cost on the main thread for unregistering objects and doing small amounts of cleanup, but the rest of the work actually happens on the background thread. So deleting objects in bulk in Unity 5 is much faster compared to Unity 4. One thing that people often don't realize, though, is that when you call object destroy, what you destroy is only the internal memory inside of Unity. It is not the script memory. So the managed objects that refer to this internal memory, they stick around until the next garbage collection, because the managed heap is entirely under control of the garbage collector. We never just go and delete objects from there. The same goes for assets. Assets are by default unloaded when we run asset garbage collection, which is separate from normal garbage collection. They use the same tracing logic, but still they're two completely separate passes. So to get in a completely clean state, where both the managed heap is completely clean of all data, as well as all the assets are unloaded, you would have to run both kinds of garbage collections. The easiest thing in practice to do is to put these in strategic places. Like if you have a loading screen, that's the obvious choice. Run asset garbage collection, or actually in that case, it will run automatically one frame later. But you can run the garbage collections there when you can acceptably wait for a bit. For assets, you have the option to actually unload them manually as well, using resources.unload. That also works from assets you loaded from asset bundles, as long as the asset bundles are still loaded themselves. If you kill the asset bundle, it will basically unregister all the assets, and then you cannot use resources.unload anymore. A downside to using resources.unload is that, well, you have to guarantee yourself that the asset is not really being used anymore. So if that is not actually true, you may run into problems. Like in the editor, you won't even notice. The editor just goes and loads the asset back in the next time it is used. But in the player, this is not the case. So in the player, if you unload a mesh and it's actually still being used somewhere, nothing will render. And I'm sure we have some asset types that actually will cause worse things to happen, and we probably won't deal with it gracefully. Also, always a good thing to keep in mind with garbage collection, it's easy to have references that accumulating somewhere, like especially if you have managers and you register something somewhere, make sure you always take out that reference again when you no longer want it to be there, because the garbage collector will actually see that reference and keep all the data alive, which in turn may cause a lot of assets being kept around even though they're not really used anymore. So let's focus on GC performance for a bit. In terms of garbage collector performance, like a good thing to know is how the garbage collector actually works. Technically, like we use the Damm garbage collector, which is if you want the full thing, like non-generational, mostly accurate, well-stop, mark and sweep garbage collector. So what does all of that stuff actually mean? The thing is, mark and sweep means that, well, let's start with well stop actually, that's the most sensible thing. Well stop means that when the garbage collector runs, we stop everything else. So all the threads that are registered with a virtual machine, they get paused, then garbage collection runs, and then we resume work afterwards. So as long as garbage collection is in there, nothing else happens. Mark and sweep means we run two phases while the world is stopped. In the first phase, we determine the set of live objects. So we start with the roots, like all the globals and the stack, and we look for references, and then we trace the references to the objects, and then we look for references inside of those objects, and so on and so forth. And every object we find, we say, okay, you are live. And then in the second phase, we go through all the objects we have, and all the ones that are not marked, we throw away, and the rest we just keep. And finally, another term that came up was non-generational. This means that we don't separate these objects into separate sets. Instead, we take the entire set of objects and we scan those. What this means in practice is that the amount of objects that you have, as well as the amount of references that are in there, directly determine the cost that you have for garbage collection. So if you reduce the amount of objects and you reduce the amount of references, you bring the cost of garbage collection down. Also, because the garbage collector actually wanders around in memory and walks all over the memory, cache performance or the effect on the cache is actually a pretty important thing and may cause slowdowns. Like if the objects are scattered around like crazy, that means the garbage collector runs much more slowly than if the objects are spaced out nicely and it can just walk over them linearly. So to optimize the garbage collection stuff, there's two angles on which to attack. Like for one, you can reduce the amount of work that the garbage collector has to do. That means bringing object counts down and getting rid of references. And you can reduce the amount of times that the garbage collection runs, which translates to having fewer allocations and not generating as much garbage. So there's a couple tips here to keep in mind when writing code that works well with a garbage collector. One thing you want to do is you want to pack your references tightly. So let's say you have a mono behavior and it has a couple of properties that reference either components or game objects or some other managed data. A bad thing to do would be to stick booleans or other value types in between them, because that means that the tracing code or the scanning code actually has to skip around in the memory. So pack them tightly together so all the references are next to each other, or get rid of the references entirely if possible. Also, while this helps with memory and individual objects, it doesn't, another thing to do that actually helps with multiple objects is to pack them together using structs in arrays instead of classes. We look at a more concrete example like in the next slide, but yeah, and that probably explains that better. And also, like the most aggressive form of optimization is actually to completely separate the value types you have from the reference types. Because the garbage collector knows if an object may contain any references or not. And if it does not contain any reference, like the cost of marking that object is very, very low. So, for example, if you put all your vectors and all your bools and all your ints in one struct and put all your references in another one, or another class, that may greatly speed up things. So let's look at a very simple but concrete example of how that looks in practice. So on the left side, you have a character which has a string property, name, and a position property. So the first one is a reference type, and the second one is a value type. And then we put all that into an array of characters where all these references are next to each other. So on the left side, like the red stuff is stuff that the garbage collector needs to look into because it contains references, whereas the blue stuff are objects that do not contain references. So you can see that in the first case, the garbage collector has to first trace the array and then find all these pointers. And the pointers lead to individual character objects, which in turn lead to string objects. So in the worst case, all these character objects are scattered around in memory like crazy. So the garbage collector has to walk all over the place on the heap. In the second case, on the right, there's only one single change. Actually, you need to look closely in order to even catch it. All that's being done there is the character is now a struct. What that means is that the memory for the character is inlined wherever it's used. So either on the stack, or in this case, it's inlined into the array. And the effect on the garbage collector is that it sees that array and sees the value type inside of it. It knows, okay, there is a reference, because we still have the name property. So it needs to scan that array. But all the data is completely linear in memory. It's packed tightly together. So scanning that array is pretty fast. Also, we don't need to walk all over the heap memory because all the different individual character objects are gone. So the right case, even with that simple change, will perform much better. So here are some results. Like running this with 1 million characters, like on a pretty up-to-date machine. A first case, like with a class, and artificially making sure that the objects are scattered around in memory like crazy. You can see it takes 35 milliseconds to do a garbage collection pass on this. The second case is still with a class, but forcing the character objects to be completely right next to each other in memory. This is something you cannot do manually from script code. This is like a fake testing scenario.